Hey there, I'm going to do a very quick recording for beginners who want to understand pi space and the idea of gravity in pi space and how it's modeled and how it's understood in pi space. We start with the Newtonian formula, which is the force of gravity. This is the version of the formula that includes the two bodies and the distance between them. You can also calculate the gravity field for a large body such as a planet. The force of the gravity. Einstein came up with the concept of a field, such as is drawn here, and the idea is that there's a gravity field, and then there's a gravity force. So the field produces the force. If that's not clear, the idea is that the field is generated by the mass of the body, and then the force is calculated by dividing the radius squared of the planet, and we multiply it by g, which is the universal gravitational constant, and that gives us this g value, which is gravity, which is also an acceleration. So uh, in pi space, the idea of acceleration is pretty straightforward. Um, the key thing to understand about an acceleration, which gravity is it's to do with an area change, per atom area change, um, and we calculate that by these two values here with times the gravitational constant. So let's take the example of how we calculate this gravitational constant for a planet such as, say, the Earth. So the diagram I have here is as follows, which should hopefully make things a bit clearer. What we have is a planet such as this one here. The idea is that you can model the planet on a pi shell, which is another name for a sphere. It can be as small as an atom, or it can be as large as a planet. Within that planet, we can model the gravitational field as follows. At the center of the planet is the center of gravity, and this is the edge of the planet. Right now, if we talk just at a beginner's level, what we have are atoms at the center of the planet, which are the smallest atoms, and at the outer edge of the planet are the largest atoms. So there's an area difference between the smallest one and the largest one. The sum of those area changes is actually the gravitational potential. As you move in towards the center of the planet, the atoms shorten, and that's the radius excess. So that's the radius excess, and it happens on a per atom level. If you move from the center of the planet up a height h, the atoms from here are smaller and they're here are larger. The difference in the area, now it's the area change, is the gravitational potential, right? Potential. So you can think of water in the dam. The water at the higher point in the dam has the higher potential energy. So when we talk about energy in pi space, we're talking about the summing of the area changes of the atoms. If we're at this point here and we drop under gravity and we fall and we increase our speed, as an atom gets smaller in the pi space theory, it moves faster. But the kinetic energy is essentially summing up the area changes. So the potential and the kinetic energy are two sides to the same coin. The kinetic energy is all about summing up the area loss because it gets smaller, and the potential energy is all about summing up the area gain. And that's why in physics, when you do a lot of calculations, you can put the potential energy equal to the kinetic energy. In other words, you're putting an area gain against an area loss. Now, it gets a little bit trickier here when we relate the area gain and the area loss to energy, but then we relate energy to well-known properties of an atom, right? Such as the clock tick, the distance travelled, and the velocity. Now the velocity is a combination of the distance divided by the time. So let's just focus on the distance, which in this case would be the height that you go up, and then the clock tick is actually the stopwatch clock tick. Now I've already explained in other lectures that the clock tick in PySpace is modeled as each atom is modeled as having its own clock tick, right? So the idea is that time isn't this other thing. The time is built into each atom. That's the core concept in PySpace. Now, if all atoms in an area have the same atom size, the clock tick is the same, runs at the same rate. If you have atoms which are smaller, the clock tick is slower. If they're larger, the clock tick is relatively faster. Now, for the purposes of our example here, we're in a weak gravity field, and the actual physical area change between the bottom, the center of gravity, and the outer part of the gravity, the area change is quite small. It's g, and it's g over c squared, right? That's your area change with respect to movement, typically of 1 meter. So that's how we model it. I won't get into the detail too much of it, but just think g divided by c squared per meter, right? That's roughly the kind of change in area. So if you take c and you square it and you divide g, which is roughly 9.8 meters per second squared, that's a tiny amount of area change. So we're in a weak gravity field. If you're in a collapsar or a black hole where the atoms shrink down to nothing, then the clock tick is something that you must take into account more seriously. But for the purposes of this discussion, the clock tick of all the atoms on planet Earth all pretty much run at the same speed, except maybe when you're on say a jet line or whatever. But even then, the change in the clock tick is quite small. But for the purposes of this discussion, the clock tick we assume is the same rate. So we have a clock tick on each atom, and then we have the distance that you move up, right? Now, one of the very important experiments that was done by Galileo when he first tried to understand gravity was he took an object, and what he did was he took the object and he rolled it down a surface, right? He rolled it down a surface, and he measured two things. He measured the distance that the object travels, and he measured the amount of time it took. And what he found was very interesting and a little bit confusing, but he wrote it down. He discovered that the distance that an object falls or moves and the time it takes, the distance is proportional to the time squared, t squared, right? So s, and the way it's described is s is proportional to t squared. S is the distance and t is the time, the seconds, which all run at the same rate, roughly in a weak gravity field. Now, the thing is that those values are related to area, to the area change, which is an energy, which is related to energy. So the way we model this in PySpace is what we do is we say that the area change is proportional to the distance that one travels. So in other words, if you are modeling potential energy, right? If you're modeling potential energy and you want to say, well, what is my energy gain if I move up height h? The formula that Newton came up with is m times g times h. In other words, g times h is proportional to the area gain as you move up. So as you move up, you gain energy. It's g times h. It's s. It's this area change. So that's like the area gain due to moving up, right? Now, let's say we want to model the area change moving down. Newton came up with the concept of the kinetic energy idea. He said it's the kinetic energy. So what you have is you typically have a velocity. You have a starting velocity of 0 and you have a final velocity vf. And what he did was he multiplied the final velocity times the average velocity, and you got 1/2 mv squared. So what we see there is that he converts the velocity, which is distance over time, So velocity is proportional to time t. So he said m times v squared. So if velocity is proportional to the time squared. In other words, if you want to convert the velocity, which has the time component into it, into an energy version, you have to square the time. You have to square the time t, because it's proportional to the diameter aspect of the diameter aspect of the sphere. So if you're not sure what I'm talking about, basically velocity in pi space is modeled as a area change, but it's a diameter change. It's measured in terms of the diameter, and if you want to get to the area change, you change it. You have to square it. So area change of a sphere is related to the energy. So when we think of energy in physics, in pi space, you map that to area change of an atom, right? So let me just try and consolidate that in this diagram here. So you're here on the surface of the planet, and you move up, and your teacher says, hey, how do you calculate the potential energy as you move up? You say it's m times g times h, right, as you move up, which is the Newtonian formula. In other words, it's the mass, which is inside the pi shell, times g, which is the area change with respect to distance, and then you multiply it by the distance h, because the area change is related to the distance. They're proportional to one another. It's simple. You just say g times h. So in other words, you're summing up the area gain. That's potential energy, right? Now let's say you're given a question which is, the object is falling down to the earth, and we know its final velocity is y, or v final. What you do is you to get the energy, the kinetic energy, if you can't go v times you don't have a distance, you don't have a time, you have the velocity. You have to square the velocity, because time is built into it. Speed is distance divided by time, right? So you have a time-based value. So you have to square the velocity. So it's 1/2 mv squared. So what 1/2 mv squared is doing is it's turning a velocity value, which is a diameter based calculation in terms of the pi shell, and it's basically turning it into energy. So in other words, 1/2 mv squared is giving you the area loss of the atom as it moves down. The potential energy is giving you the area gain as you go up. Okay, so gain up, loss down. Now the next thing to just do before I finish the beginner's lecture is you may wonder, why does the formula work at all? So I'm going to explain why the formula works. So basically the Newtonian gravity formula is the gravity constant times the mass over the radius squared. So the key thing to note here is that the mass is what generates the field, right? So we go back to this diagram. The field is this here in the Einstein idea of the field that is generated. The field is generated by the mass part, which is one or more masses. You multiply them by each other if there's more. That's how the field is generated. Now the radius, you square the radius. And why do you square the radius? You square the radius because what you're trying to do, is you're trying to build a pi shell, which is described here. And in the pi space theory, if you want to get from a diameter, which is, even though it's the radius of the planet, it's actually, this is a diameter of a pi shell, which is the center of gravity to the edge of the planet. If you want to change it into an area calculation, which is the area of the sphere, it's pi times d squared, and the radius r is the diameter of this pi shell here. So that's an area calculation here. So you get an area of this sphere from the center of the planet to the outer part of the planet. So that's what the r squared represents. So it's the total area divided by the field that's generated by the mass, right? And then you multiply it by this gravitational constant g, and what that gives you then is the per atom area change. So in other words, what this is giving you is actually the area change as you move up with respect to distance. So it's the per atom area change as you move up. In other words, the per atom area gain. That's what it's giving you. The total area of this pi shell, as I call it, or it's just a giant sphere, divided by the field, which is the mass part. The mass generates the field. So it's the field divided by the total area, giving you some value, and then the field value has to be then multiplied by a scaling constant to give it the per atom change as you move up or as you go down. And that's how gravity is described in the pi space theory. It's all to do with an atom changing its area, either gaining area or losing area, and the distance is proportional to the area, and the velocity needs to be squared if you want to go the other way. And that's gravity described in reasonably simplistic terms in pi space theory for a beginner, and it all works from there. I have other videos if you're not sure on some of the things I'm talking about with regard to velocity, but that's it. Thanks very much.